Hello, everyone, and welcome to Water Potential 101, what it is, why you need it, how to use it. Today's presentation will be about 30 minutes, followed by about 10 minutes of Q&A with our presenter, Dr. Doug Kobos, whom I'll introduce in just a moment. But before we get started, we do have a couple of housekeeping items. First, we do want this webinar to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll be keeping track of those for the Q&A section toward the end. Second, if you want us to go back or repeat something you missed, no worries. We are recording this, and we will be sending around a link to that recording via email within the next 3 to 5 business days. All right, with all of that out of the way, let's get started. Today, we'll hear from Dr. Doug Kobos, who will discuss the basics of water potential. Dr. Kobos is a research scientist and the Director of Research and Development at Meter Environment. He also holds an adjunct appointment in the Department of Crop and Soil Sciences at Washington State University, where he co-teaches environmental biophysics. Doug's master's degree from Texas A&M and PhD from the University of Minnesota focused on field-scale fluxes of CO2 and mercury, respectively. He was hired at Meter to be the lead engineer in charge of designing the thermal and electrical conductivity probe that flew to Mars aboard NASA's 2008 Phoenix Scout lander. His current research is centered on instrumentation development for soil and plant sciences. And without further ado, I'll hand it over to Doug to get us started.
All right, thanks, Brad. Good morning, all. So I want to spend just a few minutes with you guys today talking about water potential and really focusing in on its importance to you. But before we get into the meat of that, I want to talk a little bit about an experience I had. This says last week at WSU. This is actually 2 weeks ago now, but this is about half of the graduate students that we teach in our environmental biophysics course at Washington State University. And so this semester I'm teaching the lab, and you can see that we're in the lab, and we break out into small groups with all these grad students. So this is a group of grad students that are environmental scientists, soil scientists, agronomists, some civil engineers. So we get a pretty diverse group, and the lab focuses on instrumentation and measurement of the physical phenomena that we have in the environment. And so when I set about to try and teach them how to measure and the importance of measuring water potential, I gave them a question. I posed them a question at the beginning of the lab, and I said, if we have a soil that's at 10% volumetric water content, so 10% by volume water, are the plants in that soil water stressed, or are they not? And then we devised an experiment and a set of measurements, because of course it's a measurement lab, to try and answer that question. And so here are the measurements. You can see in the top pane, we measured the water content of 2 different soil samples. One of those is a sandy soil, and one is a high clay soil. Measured the water content, volumetric water content of both of those with one of the capacitance type probes, a Teros 12 in this case. And then we also measured the water potential of those 2 soil samples. So you can see in the bottom left, we measured the water potential of the sand sample with a tensiometer, and measured the water potential of the clay sample with the WP4C, which is a dew point, a vapor pressure instrument. And with those measurements in hand, we went about trying to answer the question of if the plants on these 2 soils would be water stressed or not. And here's what we found, the results. So the sand sitting at about 8% volumetric water content, and the clay a little bit higher, more water in the clay, so 10% volumetric water content. So, but pretty similar in terms of water content. However, if you look at the water potential line, the sand is at negative 10 kilopascals, and the clay is at about negative 1200 kilopascals. And a couple of things to keep in mind. First, 0 is very available, and the more negative you get, the less available that water is. And we have a couple of benchmarks that help us out with understanding water potential. And one of those is field capacity, that generally ranges from about negative 10 to negative 33 kilopascals. Okay, so up pretty close to 0. And the most simple definition of field capacity is really that is as much water as the soil can hold without the water draining due to gravity. And then on the other end of the spectrum, we have permanent wilting point, which is about negative 1,500 kilopascals, which the most simple way to think about that is, well, that's when your plants wilt and die. They start to feel water stress well before that, but at about negative 1500, you can expect extreme water stress and potential mortality on a lot of different plant species. So with that information, now we can look at the water contents, and that doesn't tell us so much, but when we look at those water potential numbers, we have one set of water potential, the sand water potential, that is up above field capacity, meaning water is plentiful in that sand and actually draining probably through the sand, whereas the clay soil at a higher water content is at the point where the plants would be extremely stressed and probably dead. And so this is a cartoon we put together of the results of that experiment, that the sand at a lower water content has really happy and thriving plants, whereas that clay soil at a higher water content, that water, despite there being more water, is not available enough to the plant, and the plant is dead. And so this is just a little thought exercise that I put the students through to try and get them to think a little bit about the difference between water content and water potential, and the reasons why water potential is a critical parameter to understand in any environmental situation. And so I gave a seminar, a virtual seminar, another webinar back, I think in 2014-ish, with a similar title to this, Water Potential 101. And in that virtual seminar, I spent a full hour, maybe a little bit more, going into some pretty technical definitions and a really thorough discussion of water potential. But then as I spend more time teaching, and especially teaching these, I mean, these are really talented grad students that we're teaching. These guys and girls, end up off, in academic careers, maybe somewhat as many of you are hoping to do, and really talented, really smart people. But what I come to find out is that, we can spend a whole semester teaching and trying to get concepts instilled in the students, but there are generally only 2 or 3 aha moments in a class that actually stick with the students, that result in lifelong learning. And those of you who teach may be familiar with this as well, that you can try as hard as you want in great enthusiasm and try and get these concepts instilled, but really it's only 2 or 3 take-home messages that the students may take away from class. And so in this version of Water Potential 101, I want to back away from some of the complexity, back away from some of the definitions. I want to back away from some of the equations. I mean, I have a soil physics background, so I like to, of course, throw equations out there because equations are really cool in a presentation, but I don't think that those really are what help cement the concepts. And so I want to keep this presentation super simple, and I want to leave you with only 2 take-home points. And so I'm going to go into the take-home points right now, okay? The first one is that water potential tells you directly if organisms are comfortable. It tells you if they're water stressed, or it tells you if they have plentiful water. Okay, no other measure is going to tell you that. It's the water potential that tells you that. And this is true for animals, for microbes, and especially for plants. So if you know the water potential in the plant or the water potential in the soil, that tells you if the plants are water stressed. And this is a key concept that many overlook. And I want to borrow a little bit from some ideas that we've been kicking around here at Meter and before that Decagon for a couple of decades now of how to try and make the concept of water potential more understandable and more broadly accepted by the science community, and also by the agricultural community, where it can be extremely useful. And what we're converging on is that you could think of water potential the same way you think of temperature. So you're all pretty familiar with the temperature that you're comfortable at, and water potential is the same type of intensive variable that tells you if the plant or the animal or the microbes are comfortable. So there's a thermometer there with some water potential units on it, and that's the simplest way that you can think of water potential. Is it's the same as temperature. And since the 40s and 50s and 60s, the body of research has been available that tells you what temperature or what water potential different plants are most comfortable at, where they thrive the most. And you can see that in the graph on the right, that there are tables in different textbooks. And I mean, you can look this up online, different water potential ranges that turf grasses do best in, or any tree, or any crop or food crop. And you can, I mean, it's well known what water potential those thrive at. And so you can use water potential as a direct indicator of the availability of that water to plants. And that is extremely powerful. So that's take home point number one. And I'm going to go over these multiple times because that helps with learning as well. The other take home point is that the second law of thermodynamics tells us that water will always move from high water potential to low potential. Things always move from high energy state to low energy state, just like heat moves from high temperature to low temperature. So you see the red hot ingot of metal and then the very cold ship. Okay, it's everybody here has an understanding that if those two were brought together, the heat would move from the hot surface to the cold surface, or the hot object to the cold object. And the same is true for water potential. Water in the soil plant atmosphere continuum always moves from high potential to low potential. And on the right, you can see that this is a passive process where the soil is at a higher water potential, the atmosphere is at a lower water potential, and so the water moves from the soil into the roots, into the xylem, through the leaves, and then out to the atmosphere, just along that water potential gradient. And so systems, all systems, natural and man-made, but we care more about, agricultural and environmental systems, they continuously move toward equilibrium in water potential. So the water will always try and move toward the lower water potential until the water potentials all equalize. And if they are able to equalize, you have steady state or equilibrium conditions, and nature is always trying to go that way. So those are the two take-home points, that water potential is your temperature that tells you the comfort level of organisms, and water always moves from high potential to low potential. And if you remember those two things after leaving Water Potential 101, then we've been successful. So the question then is, if water potential tells you pretty much everything you need to know about water and the environment, then why don't we use it more? Why is this not a household word? Why, if you were talking to laymen or many agricultural producers, would they not talk in terms of water potential? Well, I would say that we're scared of water potential for a few reasons. And I want to try and address these reasons so that we can be a little bit more comfortable with water potential and why it's important. So one of the first reasons is that it has a really confusing definition. And so if you tuned into my 2014 Water Potential 101, I would have tried to drill into your head that water potential, the definition: energy required per unit mass or volume of water to transport an infinitesimally small quantity of water from the sample to a reference pool of pure free water. What? I mean, what are we saying there? And so I've got three pictures there that kind of describe my progression in terms of water potential. I can speak from personal experience that the meme girl that you've seen on the left there, that you've seen probably hundreds of times in different memes, that was me in introductory soil physics back at A&M when Kirk Brown started talking about water potential and given this definition. I was like, what is he talking about? And then in advanced soil physics, took with Kevin McInnes, also at A&M, that was me in the middle. I started thinking about it a little bit more, but still didn't really understand what was going on, even though we were writing, models that were, 2D models that were, describing water flow in the soil in response to the water potential gradient. But I still didn't know what was going on. And then the lady on the right, who's actually studying a little bit and a little bit less confused, I would say that's me now. So I really started to get a grasp on water potential and what it actually meant and the functional importance when I came to the meter group, which was then Decagon back in 2003, and immersed myself in this because we were trying to make better water potential instrumentation. But I will tell you that I'm still probably not all the way there, that I sometimes talk to plant physiologists and they start talking about aspects of water potential that I've never considered in that living environment, in the biological and organismal environment. And so it can be a complex topic. However, it doesn't have to be. And the functional importance is what we're focusing on today. So I don't think we have to get caught up in that confusing definition. The things that we need to remember are that it defines water availability to organisms. That's number one. And the other thing is that water always moves from high potential to low potential. So if we focus on that instead of the definition, then we'll be in good shape. Other reasons why we're scared of water potential. Well, it's got a lot of different units. Okay, so you can talk about this in centibars, kilopascals, bars, atmospheres, centimeters of water. You can convert from freezing point to water potential. You can convert from osmolality or solute concentration to water potential. You can convert using the Kelvin equation from relative humidity to water potential. And so all of these different, PF, I forgot about PF, and sorry, these aren't formatted quite right. These got a little squished up, I guess. But PF, we introduce a logarithmic scale to water potential, which further obfuscates the issue. And so when we have a whole bunch of units, that causes confusion as well. And maybe the big kicker, and this is one that got me and often gets others, I think, as well, is that our scale is negative, because 0 is our highest water potential, our most available, and everything from there goes more and more negative. Okay, the drier you get, the more negative it is. So when you say things like, oh, I have a higher water potential, well, you mean a higher absolute value, or you mean higher more towards 0? So that causes confusion often, and that's another one of the things that we need to get past. The other, one more reason that we tend to be scared of water potential is that it has multiple components. So we have a matrix potential. Many of you have heard of matrix potential. Well, that's from matrix forces, or forces that have the water attracted to surfaces, which make it less available for biological activity. We have a gravitational potential. Water flows downhill. We have a pressure potential, which is that one's kind of intuitive. It's just a pressure or a vacuum, a pressure or a suction that we have to take into account. And there's also an osmotic potential, which is just attractions to solutes. And so we have these 4 different components that make up the overall water potential, and understanding where those are important in the environment and where they're not important is often intimidating as well. And then the last bit that makes water potential a little bit more difficult is that it's hard to measure. Okay, it's relatively hard to measure compared especially to water content. And so you have some instruments that are well suited for the lab, you have some instruments that are well suited for the field, you have some instruments that work in the wet end, you have some instruments that work in the dry end. And so unfortunately, there is no one instrument that is going to give you accurate measurements all the way from 0 water potential down to air dry water potential, either in the lab or in the field or in the plant. So there's work yet to be done there, but that's our job. That's our job at Meter, and that's what we're continuously working on, and we're getting pretty close to the next generation of field water potential sensors. So we will keep working on that, and by the time I retire, I won't have to make that statement. We'll be able to say, yes, we have the instrument that measures across that full range. I hope. It's a career goal. Okay, so what's the result of all this confusion? Well, what the result really is in practice is that we as a community, we as a world are still stuck on water content, especially in the soil. So in the plants, water potential is commonly measured. Well, if you're measuring water status in plants, then you're nearly always measuring the water potential. However, those measurements are difficult, and those measurements are not made as frequently as they probably should be. In the soil, we have pretty easy sensors. You can see a couple of capacitance type sensors that are used in all over the place in research and agriculture. And so water content is pretty easy to measure. It's easy to measure. It's easy to understand. We have units that are pretty, it doesn't get much less complex than percent. So we talk in terms of percent water content. And really, this is what we're used to. We've been making these measurements, since Clark Top did his work back in the early 80s to give us, a TDR type water content sensor. And so there's a lot of momentum with this. I was just talking to Georg von Unelt this morning, who is the founder of UMS that works both in water content and water potential, that now is part of Meter Group as well. And he was speaking with Harry Veriken over in Germany, who heads their whole Agrosphere Institute. And they, what did Georg say? They had 200 million euros in funding for all the projects that they're working on with that institute. And they are measuring exclusively water content still. Even though this is agricultural research, they need to be measuring water potential, and they're looking for the perfect instrument to do it. But even these guys, this is a really good research group, are still stuck on water content because it's what's always been done, and it's quite a bit easier to do. So what we need to do as a community, and what we aim to do as a company as well, and do our part in this, is try and change that paradigm. Okay, so we need to respond to these complexities and these complaints. So the first complaint, water potential has a complex definition. Well, we don't care about the definition. We need to focus on the importance, right? Not the actual definition. So what are the important things? Well, these are the two take-home points that I keep bringing up. Water potential tells you directly if the organisms are comfortable or if they're water stressed, okay? And it also tells you if the water is going to move from one spot to the other, because water always moves from high potential to low potential. And that is pretty much all you need to know in the soil and in the plants. However, I will make the statement that water content is more important for water balance. And so if you're trying to replace a certain amount of water in irrigation, then that's when water content can become important. But for the most part, water potential, just think of it as the thermometer that tells you everything you need to know about water in the soil or in the plants. Okay, so forget the definition. We have the complaint that there's confusing units, and yeah, there's a lot of units, but you can choose your favorite unit. Okay, I tend to work in kilopascals, and you can convert all those other units to your favorite unit. It's pretty simple. The conversions there are all really straightforward. And then if you don't let that negative scale intimidate you. So when we're talking about temperature, you know, both the Fahrenheit and the Celsius scale both go negative, and that doesn't intimidate us. I mean, we still understand that heat is going to go from high potential to low potential, from high temperature to low temperature. So if we think about water potential in terms of heat and don't let those negative units intimidate us, then that becomes really super straightforward. We also have the complaint that there's multiple components. So we've got matrix potential, gravitational potential, pressure potential, osmotic potential. Well, just keep in mind that gravitational and pressure potential are generally unimportant in the environment. There are, you know, some very rare circumstances where they are important. So you really only have to focus on the matrix and osmotic. And for most applications in the environment, it's only the matrix potential that really is affecting especially plant availability, unless you're in a salt-affected soil. So you shouldn't have to spend a whole lot of time worrying about the multiple components. And also, if you do your homework, and maybe if you consult with the sensor manufacturers, you can choose a sensor that measures the components that are important for your particular research or your particular applications in maybe the environment or agriculture. So hopefully we can get past these complaints. And then the final complaint, well, water potential is difficult to measure. Well, it is, but that's our job, okay? And we as a community, not just Meter Group, but others as well, are coming with new technologies every single year. So the plant water potential sensors and measurements are improving rapidly. We're seeing new technologies come out that hopefully will change the game there. Certainly the soil measurements are improving. You can see that I made a little cartoon down there with, you know, some Teros 21s and those are basically just your thermometer. And so in the sand on the left, you can see that the temperature is up and nice and high, and the water potential is nice and high, and that plant is doing really well. But in the clay, Teros 21 will measure that as well, negative 1200 kilopascals, and it'll tell you specifically that, hey, these plants are not doing well. And so there are instruments now available, especially in the soil, that can measure across the full range of the water potential spectrum that are important for plant measurements. And I think as a result of that, water potential is rapidly catching on. So kind of painted a little bit of a doom and gloom picture that, oh, water potential is tough, but it's not. It's not as hard to measure. It's not as hard to understand. It's really gaining traction. I mean, I can say firsthand, because, you know, I work for Meter and I know how many water potential sensors people are buying from us, that especially in irrigated agriculture and environmental and agricultural science, people are really starting to see the light and starting to measure water potential. And that is exactly what we want, because it tells you pretty much everything you need to know about water in the environment. So let's get back then to our third go at these take-home points. And this is the end of the presentation. It's super short and super sweet. All I want you to do is remember these two key take-homes. First, that water potential is your thermometer for water in the environment. Water always moves from high potential to low potential, just like heat goes from high temperature to low temperature. So you know where the water is going to go. You know how fast it's going to get there if you know the water potential. Water potential also defines the comfort level of organisms, or the water stress level, just like temperature tells us if we're comfortable. And so if you remember those two things, just those two things, that water potential defines water stress and water potential defines the movement or equilibration of water in the environment, then that tells you just about everything you need to know. And it's not complex. Those are very simple concepts, and they're not complex at all. And so if you keep in mind those two take-home points, if I ask you the question, or maybe if one of our biophysics students asks you the question, now I have a soil at 10% volumetric water content, are the plants going to be water stressed or not? Well, you're going to tell them, I don't have enough information. Or preferably what you would tell them is, why don't you tell me the water potential? Because then you would have all the information that you need. Okay, thanks.
All right. Thank you, Doug. And we'd like to use the next 10 minutes or so to take some questions from the audience. Thank you to those who have already submitted questions. We've got a couple questions that have come in already, and there's still plenty of time to submit questions. We'll try to take questions all the way up until we need to cut off. And if we do not get to your question, we have them recorded. And so Doug or somebody else from our Meter Environment team will be able to get back to you to answer your question directly via the email that you registered with. All right. Let's see. First question here. We've got, let's do this one. How do you recommend determining optimal ranges for specific crops not in the literature? So is this something where you ground truth with a pressure bomb or pressure chamber or something along those lines?
Yeah, that's a good question. So I think that if you look in the literature at a variety of different plants, you'll start to converge on, you know, general ranges that are best. Now, if you have a really special plant, right, if you have maybe, you know, a desert plant, then I think additional research would need to be done, and you'd probably need to do some studies where you vary the soil water potential and look at the primary productivity, or at least the transpiration rate from that plant, to try and understand when it kind of cuts out the transpiration and starts to lose productivity. But I would say that most plants have been studied pretty well, and there is a body of literature out there. So hopefully you can find yours if you dig for it just a little bit.
All right. Second question here. Does soil organic matter make a large difference to water potential? And they're asking specifically in clay soils, but how much does this matter in, you know, any type of other soils? Yeah,
so the water potential across any soil is going to vary, you know, all the way from zero, from freely available or saturated, then all the way down to air dry or even oven dry. And so it's kind of a loaded question. So any soil can be extremely wet at zero potential, and any soil can be way too dry for plants and can be air dry. So the effect of organic matter, what that is typically going to do in a clay soil is, if you have more organic matter, you're probably going to end up with more soil structure and better aggregate stability. And so then what that does is it changes the water potential at a given water content, right? So that moisture characteristic curve can change, especially in the wet end. and give you all kinds of benefits. It'll give you more water holding capacity. It'll give you better aeration. It'll give you better infiltration rate in those clay soils where your hydraulic conductivities may be typically pretty low, but it won't directly change the water potential, because it's nature that changes the water potential all the way from really wet to really dry.
Okay. This next one here. At sites where one might be measuring volumetric water content, at several depths, how many water potential sensors would be useful? Their guess is that it depends on how homogeneous the soil structure might be.
Yeah, so that is another really good question. So yes, you're going to end up with potentially layering in your soil horizontally. I mean, that's pretty common that you have the different soil horizons. And so if you're just trying to understand the water potential of the soil, you probably should measure in each of those horizons. If this is a project where you need to understand the water availability to plants, then you probably need to make sure you get those water potential and water content sensors in the root zone. So you really would want to put those in the depth of maximum rooting if this is a plant study. Also, though, even if you're just after hydraulic properties and water transport in the soil, it's the plant rooting and the transpiration through the plants that typically pull most of the water from the deeper soil layers. And so you probably would still want to make sure you have your sensors in the depth of max rooting.
Okay, next question. This is a question, there are several questions in here similar to this. What are some of the basic sensors that are now available for water potential?
Yeah, that's also a great question, and that's probably a water potential 201 or 301. But if you're talking about in the environment, I mean, the tensiometers are just brilliant sensors in the wet end. And then when you start getting toward the dry end, you generally are going to be using the vapor pressure methods like a dew point potentiometer or a thermocouple psychrometer. But then to get a broad range of water potential measurements all the way from close to saturation down to maybe permanent wilting point, you probably are going to need to use one of the granular matrix sensors like our Teros 21 that actually measures the water content of the ceramic disc that's in equilibrium with the soil, or something like the gypsum block sensors, or a variety of other sensors that either use thermal or capacitance or resistive techniques to measure the water content of a material that's in equilibrium with the water potential of the soil. And so those measurements are advancing pretty rapidly and getting more accurate with time.
All right. Next one here. Let's see if I can do this question some justice. And this is kind of a larger issue that kind of goes beyond, I think, what we can discuss here in a couple minutes. But how does one measure field capacity and wilting point, and what sensors, I think, they're asking, do they need in order to make those calculations?
Yeah, field capacity is an interesting one, because the technical definition of field capacity is the water content of a soil after it's been overwatered and then allowed to drain for like 2 days. And so to get at that, I mean, we've had students do this in the environmental biophysics class for their semester project. I mean, what you really need to do is get some water content sensors in the soil, and put a whole bunch of water on it, hypersaturate it, and then let it drain for a couple of days. However, the shortcut there is to understand that even though all the soils drain to different water content levels, the water potential level after that couple of days of drainage is going to be fairly similar. And that's why we talk about field capacity in terms of water potential, that for a sand, it's probably going to be about -10 kilopascals. And for, finer textured soils, the rule of thumb is about -30 kilopascals. So if you want to cheat, which most people do, you could bring the soil to those different water potential levels and then measure the water content and understand your field capacity.
Okay. Is it possible to correlate water potential with vegetation indices like NDVI, NDWI, et cetera?
Yeah, in many cases it is. And I think that those vegetation indices are kind of a lagging indicator of the water potential often. So, you know, for instance, if you're water stressed, if your crop is water stressed or your vegetation is water stressed, well, then the NDVI is not going to increase as quickly as it would if the plant were able to, you know, grow and close the canopy more quickly. And the normalized difference water index, that certainly is going to be correlatable to the water potential. And so, you know, there's a large body of research and a lot of people looking at these various remote sensing indices and trying to understand how these can be applied and if those are a good proxy and a good way to understand plant water status. And I don't think we're quite all the way there yet, but there's a lot of fun stuff out there, and there's a lot of hope that maybe we wouldn't have to make, you know, as many measurements in the soil and might be able to make these measurements from remotely sensed data.
All right. In addition to the water potential or water content, isn't the crop development stage a determining factor in whether the crop is stressed or not?
Yep, that is a great question. I mean, especially, so yes, let me make the statement that yes, water stress is a bit of a moving target depending on the plant growth stage, even in field crops, I would say, but some crops like grapes, where most growers, to get the best possible quality, are exercising deficit irrigation. Well, yes, then you really need to dial in the right water potential level at the different growth stage to achieve your goals. And maybe the best example of this is something that Meter's doing over on another side of the company, where we're working in indoor cannabis grows. So crop steering, where you induce water potential stress on that crop at key times to cause it to put on additional bud sites, and then you water it freely and let those buds get bigger and manipulate the water potential in those ways is really a huge asset in increasing the production of those systems. And so you can get at better quality, for instance, in wine grapes, by manipulating the water potential in the soil, and you can do the same thing for quantity of cannabis flower if you do that in the indoor environment. Okay.
I think we've got time for one or two. We'll see how many we can squish in here. This next one, does water potential vary with temperature? So is water potential the same at varying temperatures for the same soil type?
Yeah, that's a good question. Water potential does vary some with temperature. So if you hold a sample of either plant or water at the same water content and manipulate the temperature, then yes, you will see an effect in the water potential. But that typically is a pretty small effect and is typically something that we can neglect, especially in the soil, because we're talking about really broad ranges of water potential that define, you know, the water stress levels of plants, and the changes that you would see from temperature are relatively small. Now, one big exception to that is when you get to freezing. Okay, so if you start freezing your soil, then as soon as you get an ice phase present in the soil, your water potential drops off tremendously as temperature decreases. So what is it, 1.18 megapascals? So 1,100 or 1,200 kilopascals per degree C below zero. And so if you're in the unfrozen regime, it's not really that important. As soon as your soil freezes, you really need to pay attention to that.
Okay, final question here, since we're out of time, but I think this is a good question to kind of wrap up on, because it's asking about the relationship between water content and water potential. We do, for those who are interested in this further, we do have at least one other webinar that Colin Campbell presented on about working together with water content and water potential. So head over to our website and look for that one. So this question is, isn't it possible just to measure the water content and then determine water potential and field capacity using models?
Yes, so that's a great question. And there's been a whole bunch of work done creating pedotransfer functions and creating generic relationships that will allow you to convert from a water content measurement to a water potential in that soil type. And so those generic relationships have quite a bit of slop in them because there are a lot of different factors besides soil texture that affect the relationship between water content, water content and water potential. You also can grab a soil sample of your own and take it to the lab and measure water content and water potential and create that moisture characteristic curve or the moisture release curve. And that does quite a bit better in allowing you to then convert from water content to water potential. And, you know, as Brad was mentioning, there is some power in having both measures, right? So water potential tells you about the availability of the water, tells you where it's going to flow, tells you all these things, but it doesn't by itself tell you about the water balance. And so if you have the water content information and the water potential information, then you really have everything you need to characterize the water in the soil. So there is some power there. But as with any indirect technique, the less direct you get in converting from those, then you introduce some error. But I think for most irrigated agriculture and for many environmental studies and research, that's going to be a pretty powerful technique, is to use the water content along with the soil water characteristic curve.
All right, great. Thank you again, Doug. That's going to wrap it up for us today. Thank you again for everybody who has submitted in questions. There are dozens of questions that we did not get to. We do have them recorded, like I mentioned earlier. And again, Doug or somebody else from our Meter Environment team will be able to get back to you and answer your question directly. We will also have those questions available for everybody in attendance, so you can look over and see what other questions were asked and be able to check up on those. We hope you enjoyed this discussion as much, I think, as we did. And thank you again for your questions. Also, please consider answering the short survey that will appear after the webinar is finished, just to let us know what kinds of webinars you'd like to see in the future. And again, for more information on what you've seen today, please visit us at metergroup.com. And finally, look for the recording, a link to that recording of today's presentation in your email, and stay tuned for future Meter webinars. So thanks again, stay safe, and have a great day.